Hello, my name is Gernay. I'm an assistant professor at Johns Hopkins University, and this presentation discusses challenges, advances, and perspectives in performance-based design for structures in fire. Most buildings are designed against fire using a prescriptive approach. Prescriptive codes and standards prescribe generic requirements that lead to a prescriptive path to a solution. However, even for regular buildings, we do not know if the solution is optimal. We do not know the true safety margins or whether other design solutions will provide superior performance. Some of the questions that are not interrogated with a prescriptive approach are: what would happen in case of a fire? Is this the best design? Is this the most economical, the most robust design that we can come up with? What is the safety level against fire of this design? And then all questions pertaining to resilience, reusability after an event, and risk of a really catastrophic collapse. These are not quantified. Now, if we consider even more innovative structures and next generation buildings developed to achieve sustainability or resilience, there is inherently a need to innovate and come up with new solutions for these, which means that there is a lack of precedent and prescriptive codes may not be well suited to lead to innovative solutions for those challenges. How can we deal with fire when innovations may change the fire hazard? And how can we iterate towards solutions that are optimal, also integrating the fire performance? To answer those questions, we need an approach based on evaluation of the fire performance, which leads us to performance-based fire design. So here comes performance-based structural fire design. In this context, this approach is very well suited when there is a need to predict the actual performance in case of a fire. Performance-based design starts with defining the end goal. Then the engineer can leverage science-based methods and develop innovation and creative solutions to achieve these performance objectives. And as a requirement of the method, the engineers have to explicitly demonstrate the performance of the design. So frameworks have been developed, they exist to guide this process. Generally, those frameworks or those processes come in three stages. There is a need to define the scope, objectives, scenarios, and approaches for the design. And this will be a conversation with the AHJs, the stakeholders. It needs to be agreed upon by all the stakeholders before. Then the performance needs to be evaluated. So there, the structural fire engineers, fire protection engineers work to quantify those fire scenarios and the structural fire response, eventually quantifying the expected performance against the predefined fire scenarios. And third, these different trial designs which have been assessed are considered, and there is a decision on which design satisfies the performance objectives and is selected. So this method relies on the availability of models and methods to evaluate and quantify performance of structures in fire. This slide shows some key milestones in the development of these approaches. It is certainly not exhaustive, but you see here some of these key steps either in research or incorporation in building codes. Notably, there have been developments of software to support this evaluation of performance, including software to model the fire action and then software to model the structural fire response, such as finite element software. The performance-based design approach is an alternative to the prescriptive design approach, meaning the two coexist, the two can be used, but the performance-based design approach requires more effort on behalf of the engineers and the stakeholders who have to review and approve the design. So a legitimate question is to ask whether this is worth it, whether we really need this approach. And I would argue that yes, certainly it does bring a lot of value. And to support this, we can look at lots of examples where performance-based design for structural fire engineering has been used. We see that there are a number of situations where the approach brings values. For example, when there is a need to explicitly quantify the fire performance and fire risk. The approach has been used also to enable designs, to think about architectural preferences, having steel exposed in these type of applications, to assess existing structures, to control the failure mode, making sure a structure would fail inward and not endangering the surrounding structures, to demonstrate stability to full burnout, and to develop design methods. For example, to optimize design, there have been many cases where the so-called tensile membrane action was taken advantage of in the design, and it was found that it is unnecessary to protect individually all horizontal steel members in the building, but instead structural robustness and structural fire performance could be achieved to membrane action in the composite slabs with sufficient steel reinforcement. So this behavior is well known since the Cardington fire test in the 1990s. It has been implemented now in many designs, and so it leads to economically more optimal solutions, but also very robust designs. As an example of forensics, recently there was a fire during the construction stage of a New Zealand International Convention Center, and after the fire, there was a need for analysis to understand the damage and residual capacity of the structure, and performance-based fire design techniques and modeling came to support those decisions. For the structural fire engineer, in order to enable this performance-based design approach, the crux consists in being able to evaluate the structural fire performance. The engineer will need appropriate data, models, and methods to conduct this assessment. The behavior of structures in fire is complex. Not only are the materials damaged due to elevated temperature, but there are also lots of non-linearities. There are thermal expansion strains that create redistribution of forces. And so the structural system response is relatively complex. As a result, performance-based design requires integration of multiple capabilities in terms of knowledge of the material and structural response and modeling software. Now let's discuss some recent selected efforts towards enabling this evaluation. A key component consists in characterizing the response of materials at elevated temperature. This is not new. There have been tests on steel and concrete at elevated temperature for decades, but this is a continuous need because first, new materials continuously emerge, and second, demands on those structures in fire also evolve. Nowadays, we want to be able to assess the response until full burnout. That includes measuring properties during cooling and in the post-fire stage. We also look at expanding the capabilities of our finite element software. So when we model an entire steel frame structure, we want to capture ductile fracture. But this requires characterizing the response under multi-axial stress state at elevated temperature. And so this is still new research that is needed there. For example, in our team, recently, we characterized the response of new high-strength cold-formed steel that are coming to the market that have not been studied at elevated temperature before. We also worked on characterizing the response of concrete during the cooling phase in collaboration with Professor Bamonte at Politecnico di Milano. And after conducting those experiments, we developed constitutive models. We propose the relationships for implementation in standards and building codes, and we incorporate them into finite element software such as Saphir so that engineers can run simulations with these new materials or with these expanded situations, including cooling. Another key component in evaluating the structural fire response is having the ability to simulate the response of an entire structure. So there, a lot of work has been done to advance finite element software, notably to make sure that those software can combine different types of elements, can characterize the thermal response and the structural response, and also that they incorporate interfacing with advanced fire models, new temperature-dependent material models, and more recently, being able to conduct probabilistic analysis in order to support risk assessment of structures in fire. This work to advance numerical modeling to simulate the response is also continuously advancing, and there are continuous needs. For example, whenever a new structural system is developed, there is work needed to make sure we can model those structural systems. But also with existing structural systems, there are research questions that are regularly investigated. For example, recently we modeled full-scale fire tests conducted at the NIST on steel concrete composite floors, where the experiments looked at the comparison between prescriptive and performance-based design for the floor system in fire, including the development of tensile membrane action in the performance-based design. And we modeled those tests in order to gain further understanding on the reinforcing steel details that are optimal for the system, but also more broadly to characterize the economic impact of the performance-based design. And this entails studying the performance of those two designs comparatively against a range of fire scenarios and quantifying damage and losses in a probabilistic framework for those two designs comparatively. Question we want to answer is, over the lifetime and on average, if either design is applied, which one brings the most economic benefits in terms of fire resilience? The concept of looking at probabilistic risk analysis and multiple fire scenarios is really a key advantage of performance-based fire design. With this approach, the structural response is quantified, the safety can be evaluated. In this study, for example, we looked at a multi-story steel concrete building and we designed it considering different performance objectives which were predefined in terms of scenarios such as fire spread across multiple floors, as well as probabilistic severity of the fire as correlated to the percentile of fuel load distribution in the room. And we can run analysis for all those scenarios. We can look at different trial designs in order to derive the optimal design in terms of detailing of the section dimensions, the reinforcement area in the floor, and so on. And then we can validate the performance of the selected trial design against all those scenarios in full-scale numerical models capturing the structural system response. These probabilistic risk assessment studies allow us making informed decisions which account for all the uncertainties in the process. There's been a lot of work done recently to characterize the uncertainties, such as in collecting fuel load data and providing probabilistic distribution for those data. But we also worked on uncertainties on the live loads during a fire event, on the material response for steel, concrete, and timber properties at elevated temperature, and so on. So when we develop better data for all those inputs, as well as the capability to run stochastic finite element simulations, we can now characterize our structural fire response in probabilistic terms and generate fire fragility functions that quantify the probability to reach different damage states in case of fire, accounting for all uncertainties and for different types of designs. So those fire fragility functions can be developed for different prototype buildings and different nominal designs. In the end, our efforts in the field of structural fire engineering parallels those made in other fields such as seismic engineering, where the PEER framework is now widely used in order to account for uncertainties across the process, from the hazard characterization all the way to the loss analysis, which in the end can support rational decision-making for the design. I will now say a word on the perspectives in this field and using those methods. One key research question that we are looking at as a field now is to work toward multi-hazard resilience. We recognize that fire is a very important hazard for structures, but so are other types of hazards. Now, an optimal design obviously needs to address all those hazards, and there are situations where it's important to consider sequentially several hazards. For example, we look at the effect of an earthquake on the fire performance of buildings. Indeed, if there is an earthquake striking a large city, there will be hundreds of thousands of buildings affected or damaged by the earthquake. And it's important to know whether repairs, rehabilitation is needed for all those buildings in case the fire protection systems are compromised or the fire performance is compromised. So as part of this effort, for example, next year, there will be a 10-story cold form steel building test on the shake table at University of California, San Diego. And following this earthquake testing, there will be live fire test in the building where we will look at the fire performance of the systems, including fire protection system, gypsum, panels, and so on, in order to understand the structural fire performance of those buildings after an earthquake. More broadly, what's important is that the performance-based structural fire design can aim at integrating the fire design with other load cases, identifying the overall optimum design, and coming up with solutions that are robust even in case of sequential hazards. Another important perspective for the field is to address the fast innovation that is made in order to address the climate crisis and the development of new biosourced material or the use of existing biosourced material in larger and taller buildings. Those innovations may bring in new fire hazards. These cannot be interrogated using prescriptive design. With new structures, new solutions, we need analysis-based methods rooted in the fire dynamics and structural mechanics in order to understand the response and the safety level. So a lot of the techniques we've described, characterizing the material performance, simulating the structural response, bringing in probabilistic risk assessment, these will be very helpful and needed in order to develop fire-safe, sustainable innovations. So as part of this research effort, we are notably looking at new experimental tests on timber glue lamp columns, which are loaded and subjected to a fire, and we study their behavior until full burnout to understand and develop designs that could survive the entirety of a fire event. So as we've discussed, there have been lots of advances in performance-based structural fire design. The approach has also already been used in many countries around the world for many types of applications. However, some challenges persist. There are technical challenges, education and competency challenges, and political challenges to broader adoption of this approach. Technically, there are still some phenomena that are poorly understood. There are still some research need to characterize structural fire response. And also there is a challenge with the computational cost and complexity of these models, especially when we want to make sure the assessment is robust and capture uncertainties and capture various scenarios. There are perspectives to overcome those challenges, and research is continuously developing. There is exciting research being done on mass timber buildings in fire in order to bring those solutions. There are also opportunities with the combination of physics-based and data-based models for some questions that have been intractable for a long time. Maybe machine learning and data mining can now help do a breakthrough combined with a deep physical understanding of the processes. There are challenges in education and competency. Structural fire engineering is not in common civil engineering curriculums. There is also a lack of awareness of the potential benefits on the part of stakeholders, and AHJs can be wary of going to that road because it's another responsibility and it may be hard to identify reviewers for the designs. So in order to overcome those challenges, there needs to be a work done by the profession, and maybe to work toward definition of core competencies, accreditation. There is also a need to educate a critical mass of structural fire engineers through new curriculums, because as more engineers become familiar and proficient with those methods, that will help also developing a robust ecosystem. And finally, there is work to be done to demonstrate those benefits and raise awareness and show all these examples of structures in which this method has been successfully implemented to the benefits of all stakeholders. To conclude, it is clear that fire hazards govern many aspects of design in a building. It also is a key consideration for a lot of innovations in terms of building materials or building structural systems. In that context, the performance-based structural fire design can deliver a lot of value and support innovative solutions, because that is a method that is goal-oriented and that allows explicitly evaluating the performance of the system in fire. It has been already implemented in numerous field projects. It is meant to live alongside a prescriptive design for regular and common buildings, but it could be made more mainstream and be more commonly applied, and that would add value. But there are challenges to overcome to make that possible, notably technical, political, and education challenges. In this presentation, we showed that there have been a lot of advances in the field and continued advances in supporting performance-based structural fire design, can play really a key role in enabling sustainability and resilience innovation for the built environment. Thank you for your attention.